Dr. Saha entered into the registrar's office and told me curtly that the rules require that I must work with the head of the department, that was Saha. If I found that not to my liking, he told me to seek a job elsewhere. Raychaudhuri was the spark. I mean, his equation was the spark which lit off this thinking in their brain about singularities, because that equation sometimes tells you under right conditions that two points may feel well separated, but in the future the points will collide.
So today I'm talking with Professor Sunil Mukhi about that equations, the conditions under which it was written. So Professor Mukhi, welcome to the podcast.
Thank you.
So, before we get into history, can you explain in simple physical terms what the Raychaudhuri equation is saying? Like, if we avoid mathematical symbols, what is the basic idea?
Sure.
Like,
Sure.
as as I understand, instead of following one particle, we look at the whole family of nearby particles, freely falling particles,
Right.
and or say
Right.
light rays, and ask whether the that family is focusing or spreading out. So, is that right
Right.
way to picture it?
That is the right way. Let me try to put this in some context. You
Yeah.
see, Einstein's main discovery, if you want to really put it in a few lines, is that gravitation is described by geometry of space-time. And if that geometry is curved, in a general sense, curvature, we know what it means for space, but here curvature can mix space and time also. That general curvature creates all the effects, all the possible effects that we call gravity. So it is the underlying formalism for gravity. So Einstein did that, and of course, then it had many predictions for various phenomena, and they were tested, and so it became a very successful theory, and it's accepted as the correct theory of gravitation today, supplanting older Newton's theory. So far, so good. Now, what is the underlying object in Einstein's theory? It is what is called a manifold. It's a mathematical construction, and it's a way to make more general what is our idea of a ordinary space. So ordinary space is a manifold, but it's a very simple manifold. If you take, for example, the surface of a ball, that's a manifold also, but it's a little more complicated. For example, on that manifold, if I travel in one direction, I'll come back to where I started. But in our normal space, if I travel in one direction, I don't come back to where I started. So there are different manifolds have different kind of properties. But the manifolds are defined as a collection of points. Okay, so geometry is nothing but collection of points which have some smooth relation with each other, and that's great. And Einstein explained very well how that works. But there's an additional thing you can do when you have a space-time manifold, which is to ask not how are the points connected to each other, but also how do the points themselves move in time, because time is part of space-time. Okay, so this leads to the study of trajectories. Trajectory is nothing but the line that you draw when something moves in time. It's important to realize that even now you and I are undergoing a trajectory. Like I'm sitting in one place, but time is evolving. I can't stop time.
Yeah.
So 1 minute later, I'll be in the same place. But during that time, I have traced a line along the time axis from 0 to 1 minute.
Yeah.
Okay. So these are the lines that I follow, but it's not because I'm trying to do anything. The line is in space-time and it is evolving because space-time is like that. Because time evolves, every point goes somewhere in the future and every point came from somewhere in the past. Okay? I hope this much is clear. I tried to put it very non-technically. Now, we are asking about the relation between points, like how do points fit together to form a manifold. But now what I can do, take a region of this manifold and allow it to evolve into the future. Don't do anything to it. It evolves because time evolves. And because of the geometry of space-time, that evolution will be determined. So if I know the manifold, Einstein tells me how to find the manifold, I have to solve his equation. Then that manifold, its spatial section will evolve as time goes forward. And if I can also go backward and say, okay, what happened in the past such that we reach the manifold which we are living in today? So this is this is a study of lines which are naturally undertaken by a free particle. And those lines are called geodesics. Geodesic is sometimes used to mean the shortest path. The old language geodesic came from some, people going on ships trying to find the shortest path from A to B. They realize that Earth is curved, so it's not as simple as you think. So I have to work out mathematically on a map how to achieve the shortest path from A to B. That's a geodesic in space. But with Einstein equations, it became important to study geodesics in space-time. And this is very different concept. And Raychaudhuri, I think, understood, he was grappling with a problem, which is that the universe, if we go into the past, if we study the evolution of the universe in time, that is called cosmology. Cosmology is just the study of time evolution of the universe. Okay? And there were many claims that if you go into the past under some conditions, the universe itself can collapse to a point. Because the universe is found to be expanding. And so if it's expanding in the future, it means, and here is a very important point, the universe expanding is not the same as if you and I are in the same room and we walk away from each other. Okay, our distance will separate, but it's not because of anything the universe is doing. It is our choice to walk away. But when the universe expands, every point moves away from every other point. That's a very difficult concept, but the analogy people give is of a balloon. If I take a balloon and I blow it up so that it doubles its radius, then if I had marked 2 points on the balloon, any 2 points, then as I blow up the balloon, those 2 points are at a larger distance from each other because the balloon has become bigger.
Yeah.
The points didn't do anything. In a way, you can say they are the same points, but they separated their distance. So every pair of points is separated, and this is what we know of our universe, that every planet, every star, every galaxy, particularly galaxies, they're just moving apart from each other, and that is the expansion of the universe into the future. And question now is, supposing I look in the past, if something is separating in the future, it must be coming back together in the past. So maybe very long ago, all the galaxies had crunched into one point or into a small region, and that became the root of an idea called the Big Bang.
Yeah.
So it's a very simple idea, but it's also very subtle because it's an idea about space-time geometry. And Raychaudhuri began to ask the question that what type of space-time geometry or what conditions on space-time geometry will make this kind of behavior possible.
Yeah.
So that's the abstract question which he was the first to focus on, but the calculation he did is so simple that Einstein could have done it or anybody could have done it in 40 years between Einstein's 1915 paper and Raychaudhuri's 1955 paper. It was not a difficult calculation because all he did was to take Einstein's equations and rearrange the terms in such a way that now the same equation describes the evolution of points, what he called the expansion. Okay, it describes the expansion as a function of time in terms of the geometry right now. So if I know the expansion rate now, then I know the expansion rate in the future, or I know it, or I might get it approximately. But his interest was to just formulate the right equation which talks about that expansion rate. And then he left it there. Actually, he didn't do more. But I think for Penrose and Hawking, especially Hawking, reading that paper set off a flash in his mind. The right way to study the universe is to ask about the expansion. to calculate the expansion, write a formula for it, and study what that formula predicts. So that's my summary of what Raychaudhuri actually did. It's a hardly 3 4 5 page paper, and it has
Yeah.
one key equation called Raychaudhuri equation, and it just tells us geometrically how pairs of points, or rather how the metric or the distance measure in that space time changes into the future or into the past, changes with time.
So, I came across a historical fact that I want to clarify. So, the equation is sometimes called the Landau-Raychaudhuri equations. Like if you read the book, The Classical Field Theory, The Classical Theory of Fields by Landau, there the equation appears in some different notations. So, how close was Landau to Raychaudhuri equations? Was this essentially the same, like same focusing insight in different notation, or Raychaudhuri contribution was conceptually different?
You see, the words that Raychaudhuri uses are words that are borrowed from dynamics of fluids, which is a much older subject of physics. General relativity came only in 1915, but fluid dynamics was there for centuries before, because after all, water or fluids were always there, and people
Yeah.
wanted to know how fluids flow, and that is fluid dynamics. So, as I understand it, Landau talked about physical quantities in fluid dynamics, and they have names like shear. So, shear viscosity is a kind of viscosity. So, the word shear, rotation, and the idea there is that I have a fluid, so it has particles. Now, can I predict under the motion, the flow of this fluid, that let's say I pick any two particles, after flowing for some time, would they have twisted around each other?
Yeah.
You see that? Just follow 2 points. The fluid has lots of points, infinitely many points we imagine, because it's a continuous system. Actually, it's some number of atoms, but we treat it as continuous. But the points don't, if they are separated some amount, then as the fluid flows, they don't remain separated the same amount. They may come close, they may go far, they may twist around. And we need mathematical quantities to describe all these possible behaviors of fluids. And words like expansion and shear and rotation, which is also called vorticity, these are all words that I'm sure Landau had and that Landau studied, and that maybe other people doing hydrodynamics must have also studied.
Yeah.
Now, what is the key difference? The difference is that in the fluid case, we actually have particles, and we are asked, and the behavior of the fluid depends on the fluid itself. After all, water has a different behavior from oil. Okay, so it's some material particles, but the way to parameterize their behavior comes from, probably from people like Landau, thinking let's ask independent questions whether the particles converge, diverge, rotate, or whether one plane of the fluid slides with respect to the other, that is called shear, things like that. So the fluid thing was known. Raychaudhuri's insight was to realize that that is what we need to describe the behavior of space-time points. There's no fluid. The fluid is an analogy. Even
Yeah.
now people work on the fluid analogy of gravity, but it's only an analogy. Gravity is not literally a fluid.
Yeah.
It's literally a space-time. It's a very abstract manifold, and that's all it is. There's nothing more to it. Now you can study some things that gravity does in the language of fluids. So my sense is, I could be wrong, but my sense is that Raychaudhuri in some way borrowed the language of fluids. But the insight, as I told you, it was not that his equation was some masterpiece to derive. It's subtle. It needs you to know general relativity, but it's not something. It's impressive since he was, I think, self-taught in that field, but it's not something that, any beginning graduate student can work out that equation as he worked it out. You choose a coordinate system, you define the expansion, shear, and vorticity, and then you break up the flow of particles in space with time into these quantities and separate them, and that's the Raychaudhuri equation. It's quite simple. But it's unprecedented to think of flow when here the flow is just of abstract points of space flowing into the future in time. They are not being asked. It's not like a fluid flowing which needs something pushing it, like gravity or a river rolling down or a waterfall rolling down a hill. There's nothing like that. Here, the flow is the abstract movement of all particles in time. And as I told you some time ago, we don't have any choice whether we move in time. We just move in time.
Yeah.
Time just evolves. It's not our
We
choice.
can control moving space, but not in time.
We can control moving in space exactly, but not in time. Actually, it turns out that by moving in space, we can change our moving in
Yeah.
time a little bit. But that is the twin paradox. But as you said correctly, what we control is only our movement in space. Time just does whatever it does.
And moving in space can also affect moving in time. That's a different thing.
It, it affects moving in time, and this is why we have things like twin paradox.
Yeah. So the motivation for Raychaudhuri in the first place was not black hole. So it was cosmology, as you said. He was
It
thinking
was
about, moving backward in time. So, he wanted to know whether rotation or, cosmological constant could let the universe ever had a beginning, as you said.
We thought without cosmological constant because he didn't actually resolve the question. He basically formulated the question, and in that question, you can put the cosmological constant or you don't put. The question is only what is the expansion as a function of the curvature of space-time and the shear and the vorticity. So Einstein's equation has basically two terms. One term comes from the curvature of space-time, and if that was the only term, then Einstein equation tells us that curvature of space-time is influenced by the matter distribution in space-time. There's a very famous sentence due to John Wheeler, which says matter tells space-time how to curve, and space-time tells matter how to move. So it's a coupled system which each side influences the other, and the Einstein equation is traditionally written as curvature of spacetime equals some quantity called energy momentum or stress tensor of matter. These are equated. That's Einstein's equation without cosmological constant. If you put the cosmological constant, there's a new term on the left side of the equation. So matter now influences both the curvature of spacetime and this other term, which doesn't in fact have to be even constant, I suppose. So, and the combination of curvature and this cosmological term influence the matter. And the key difference is that cosmological term gives a different evolution from the one you would get if it was not there. So, for example, today we believe that cosmological term is there and it is positive. Only because it's positive, the universe is expanding.
Right.
So, the term has an effect. But Raychaudhuri, now I can't remember if he used it or he didn't use it, but it's not very important because he anyway just used the Einstein equation and manipulated it to talk about the expansion of the universe.
So,
And how the universe expands, obviously the cosmological constant will influence it and the curvature will influence it.
so why it took so many long time after 1915 paper of Einstein? Like there was the good mathematicians, some good physicists, like Roy Kerr, or we can take David Hilbert. They were good mathematicians, so they could have done this, but we see
As
only.
I said, anybody could have done it, and today any graduate student can do it. But in physics, often the breakthrough is not the equation, but thinking that this is an equation worth studying or it's a question worth studying. So the breakthrough is the question.
The problem you
And if
choose.
how you choose, what question you think will tell you the answer to a problem. And let me, since maybe your viewers are interested, let
Yeah,
me just
please.
digress to say that, in my opinion, because of the advent of AI, the entire aspect of doing the hard calculation is going to fade away because it can do a hard calculation much faster than you and I can even think about doing it.
Yeah.
And as it gets better, it can also not make mistakes, which we will always make. And it can also check for mistakes, which again we find hard to do. But asking the question, what is the question which we would like to understand? That is the human contribution, and I believe that one will last into the future. So, in a way, Raychaudhuri obviously died long before AI became anything, but maybe he would have liked it because he was not a technician who was very good at, I mean, he must have been good and he was a great teacher, but he must have been very good. But he was, let's just say Hawking was somebody and Penrose both were of next level in their mathematical sophistication. Their papers are very difficult to read. Raychaudhuri's paper, not so difficult, not at all difficult in a way. Hawking and Penrose's subsequent papers are super difficult. I mean, Hawking and Ellis's textbook on, what is it called, space-time, large-scale structure of space-time, still a nightmare, it's just a nightmare. Every page is so hard to understand, because it's dense with technicality, and of course that was what made them great, not trying to deny the value of it. But Raychaudhuri was before them, and he just thought that this is what we should look for. As I said, he
Simplicity.
didn't
Simplicity in the equations. He found that.
simplicity in the equation, absolutely simplicity. And one very interesting thing is that when soon after, I mean, maybe 6 or 7 or 8 years after Raychaudhuri, Penrose wrote his paper.
Yeah.
Before that, let me also give credit where it's due. Sachs wrote a paper also about the same equation, and so he's an American, and so Sachs and Raychaudhuri came to their equations independently. But there was one difference. Raychaudhuri's equation was about the evolution of material, of what kind of trajectories a material particle will follow, that a particle with mass. And Sachs's question was more focused on what a light particle of light, a photon will follow, particle with no mass. And it turns out there are two different equations. They are very similar, but they are different equations. So the one for particle with mass is the original Raychaudhuri equation. The one for the particle without mass is the Sachs equation. But
So,
often
like
called the
light.
Raychaudhuri, because of light, but often called the Raychaudhuri equation or null Raychaudhuri equation, because light follows null trajectory. So it's sometimes called the null Raychaudhuri equation. But Raychaudhuri himself, a very sweet man, said once in an interview that I don't know why they credit me for that equation. I never wrote that equation. I wrote an equation for massive particles, and they all did fancy stuff after that, but they keep giving me credit for this null equation also. And in a way, I think Sachs would have some reason, if he were around, to complain a little bit, because people don't know that he's the one who did the light-like trajectories. Now, the important difference is that it was Raychaudhuri's equation which was used by Hawking to
Yeah.
ask the question that if we go back in time, does the universe come to a big bang? Does it all collapse? But it was Sachs's equation that was used by Penrose to ask that if a light ray is trapped inside a black hole, is a light ray trapped inside a black hole in the first place? Can a light ray escape from inside the horizon of a black hole? It was really Sachs's equation.
So there are two things. One where Raychaudhuri, taken the mass particles, and Sachs took the light into the
Yes.
equations.
Yes, exactly. Now, they're not that different. I mean, if you know how to do one, you can do the other, but they are different, and the applications are different. And as far as I remember, Penrose used Sachs's equation, and I'm not even completely sure if he credited Sachs or he independently found the equation. Penrose has this, basically the Nobel paper, it's only 3.5 pages, and from 63 or something, you might know better, within 1 or 2, maybe 61, I can't remember. And
65. It's 1965.
65, okay, Penrose was 65, but he definitely didn't credit Raychaudhuri, that I remember. And probably didn't know it also. I don't know. Raychaudhuri published in Physical Review, but maybe Penrose didn't know of it. Hawking, on the other hand, my impression, now who are more expert in the field may contradict me. It was Hawking was really carried away and thrilled by the equation. Because first of all, it allowed him to do his paper, and his paper didn't rely on Sachs's equation. It relied on the real Raychaudhuri's equation. And it's the Hawking singularity theorem that if the expansion is positive today, then going back in the past, there has to be a big crunch. So everything has to come together. That's what we call the Big Bang. Okay.
So
Now later, around 1970, Hawking and Penrose combined forces. Till that time, Hawking was working on cosmology and Penrose was working on black holes. But by 1970, they wrote a couple of papers together where they did a unified treatment of the cosmology problem and the black hole problem. And there, I think they gave rich credit to Raychaudhuri. And ever after that, they were always known to say that Raychaudhuri was the spark. I mean, his equation was the spark which lit off this thinking in their brain about singularities. Because that equation sometimes tells you, under right conditions, that two points may feel well separated, but in the future, the points will collide. And as I have tried to emphasize, it's not the same as points colliding just because, let's say, I'm moving my fingers and they collide. This is something I'm voluntarily doing. It's not something that space-time geometry is making me do. What would be really amazing is if I keep my hands like this and I sit completely still, and tomorrow I find that my hands have touched.
yeah, like we take the example of globe, like we start moving in parallel lines, and at the end we met at one point.
Yeah, but that's not the same because that's still not in time. That's still a motion on the space.
Yeah,
The really amazing thing is that I don't move. I take 2 points and I just fix them. I don't do anything. Let's say I put 2 nails in my building wall, in my room wall. I hammer 2 nails into the wall. They are 1 inch separated. And I do nothing. Tomorrow I come back and I find that those 2 nails are touching each other. Not because anything happened to the wall didn't break, the wall didn't deform, there was no hot or cold weather. It's just that space-time evolved in a way, of course, not only the nails, then everything will be crunched. Everything between those 2 nails would also be crunched together. And we don't know exactly what impact that would have. But the point I'm making is that it's not because the objects material change. It's nothing to do with the material as such. I mean, the material influences how the space-time evolves, but those 2 points which were separated, they become the same. It's crazy to think how 2 points of space or space which are separate can become the same point after some time.
what is affecting this? Like, what is causing this to
The
become?
evolution of space-time according to Einstein's equations. From this point of view, Raychaudhuri's equation is nothing more than Einstein's equation. It's just a way of rewriting Einstein's equation. And Einstein's equation says that whatever the matter distribution, space-time will evolve according to certain laws. And he wrote those laws. So I can solve his equations are just some second order differential equations. If I'm very smart or if I use AI, I can integrate those equations and find out exactly what the space-time will be doing tomorrow. Now, of course, I'm exaggerating because nothing happens between today and tomorrow. Space-time is not evolving that fast because it's really the cosmological evolution, and that is very slow. That takes millions of years. So the Big Bang, if it was there, maybe a billion years ago or more. So it's not like 2 points of space which I anchor, they will merge in the past, yesterday or day before. They will merge in the past very far back. But the important point is that their merger is not a merger of two material objects, but a merger of two abstract points in the manifold called space-time.
So Raychaudhuri original question was about the past. Did the universe, have to
Yes.
begin in singularity? And
Yes.
Penrose, like, is the mirror image, you can say, about the
It is.
future. About the future,
It
like
is.
there's a
But also,
collapsing. Yeah.
yes. But it's also about you're completely right. It's about the future, but it's also about the black hole. So it's not just what the universe will do in the future, because from what we know, at least for a long time, the universe will keep expanding, which is quite boring. We'll just all move apart. The fun comes when we move together, because if you move together, you collide. If you move apart, you never collide.
About the same thing about black holes. So Oppenheimer-Sidner's 1939 result was also about, spherical star collapsing. So what is the
Absolutely.
difference between Penrose and, Oppenheimer and Sidner works?
Absolutely. Absolutely. So Oppenheimer and Snyder assumed a spherically symmetric mass distribution, perfectly spherically symmetric, and they concluded that if it collapses, it forms a black hole. And the question was, does our universe contain any black holes? For which they had no answer, as far as I know. Does our universe have a single black hole, or this is just some equation that I found by solving Einstein equation, but this never happened in our universe? Now, obvious objection, and this, by the way, was Landau's objection. I think Landau and Lifshitz, or no, sorry, it was Lifshitz and somebody, not Landau. Lifshitz, the same Lifshitz of Landau Lifshitz, with somebody else whose name I'm now forgetting, maybe Khalatnikov. I think Khalatnikov, Lifshitz and Khalatnikov. Argued precisely that, look, Oppenheimer, Snyder, that is all very dramatic, spherical shell collapsing. But where in nature do you find an exactly spherical shell? There's no such thing. It can't be exact. So it's like a very mathematical approximation that something is completely symmetric. And the symmetry is the reason why it collapses to form a black hole. If that is the case, then obviously you can't expect that a neutron star or something will be completely symmetric so much that it collapses to be a black hole. It might, some asteroid or some rock might hit it, and that will be enough to destroy Oppenheimer and Snyder's prediction, because their prediction doesn't hold if the spherical symmetry isn't there. And now we come to Penrose. So Penrose said, maybe there's a reason in underlying mathematics, in fact, in underlying topology of space-time, why even somewhat general matter distributions which are not spherically symmetric, or which you might say they are close to spherically symmetric but they might deviate a little bit, why they should form a black hole at all. And what he showed is that, in fact, they do form the black hole even without being spherically symmetric, quite generically, if they form something first called a closed trapped surface. So, trapped surface was the concept invented by Penrose. And for a trapped surface, you should imagine something like a sphere. But the weird thing about that sphere is that space-time geometry is twisted inside it. Outside it, the geometry is quite normal. Approaching that, it's strange. But inside, it's twisted in such a way that if you try to go inward, you go inward to the center of the sphere. If you try to go outward, you're still going inward. There's no direction outward. And it's not that the force of gravity, I mean, you could say that physically it means the force of gravity is so strong that it pulls you back. That's not wrong. But in Penrose's picture, it's the twisting of space-time which makes all directions point only inwards. You could imagine somebody trapped in a room who wants to escape, and maybe the room doesn't have any door, but it has thin walls. So that person feels that if I can go to the wall and break it, I can get out. And the person finds that one of the walls is solid, and these other thin walls, they approach it, but they never reach there. As they approach it, somehow the whole world twists around them, and they end up always hitting the brick wall. There's no other way to go. They just can't reach this exit. There's no exit. In principle, even. And it's not about how fast you travel. And that's why Penrose used light, because if light cannot escape, then nothing can escape. So he used light. And to use light, he needed to know the motion of light rays into the future. How light rays, whether light rays converge or diverge due to the space-time geometry. Again, remember that in real life, light rays converge or diverge usually because there's a lens. It's a material object we
Yeah.
put in their path. Because of the lens, they converge or they diverge. If you left them to themselves, they would just go how they go. If they were parallel, they would be parallel. But space-time geometry makes it such that they may be forced to converge, and every light ray may be forced to converge, not just the light rays going into the future. So you see, this is the key point is that from any one point in a trapped situation, there's always an inside and an outside. So I should always be able to find my way outside. And what he showed is with his trap surface is there's no outside under some conditions. And that situation with no outside, that is when the black hole is going to form and there's nothing you can do to stop it. And therefore, what we learn is that now, if lots of rocks and planets, and not planets, but stars, are traveling around the universe randomly, colliding with each other, also exploding, I don't know, becoming supernova, leaving behind some remnant, whatever they are doing. But at the end of it, when they become very dense and start collapsing, we don't have to ask for them to be, nobody has, God doesn't have to come and make them spherically symmetric. They will be, they will be what they are. They may have mountains, valleys, hills. But once they form a trapped surface, it's over for them. They become black holes.
Yeah.
This Penrose added, and without it, we would have no reason to think the universe is full of black holes or even has one black hole. And at least when I went to Stony Brook for my PhD, 76 to 81, of course, people who knew Penrose's work, which were, by the way, very few, only relativists really knew it. I would say nobody in my department had read it. Nobody talked of Hawking, though they were working on supergravity, which is a form of gravity, but nobody was talking about Hawking or Penrose's work. If you didn't know that, so somebody like Steven Weinberg, a particle physicist,
Yeah.
his textbook, which I think is already from the 70s, kind of leaves it very open, saying maybe black holes don't exist in the universe. They are just some mathematical curiosity, because why should they form? So
But
the attitude was that black hole is at best an exotic object. And today the attitude is that, well, we have seen black holes. Penrose told us why. And the people who shared the Nobel Prize with him are two people who actually did the observations,
yeah.
conclusively proving two particular, or one, I don't remember, black hole at the center of a galaxy. And so he brought the subject from exotic to mainstream.
So there is something I want to read because what we're talking about. So this is Friedman Dyson, writing about why Einstein and Oppenheimer both lost interest, or Einstein case where black holes later in their career. So no, Einstein treated black hole solutions as a as blemish in on theory, something to be mathematically fixed away, not a prediction to take seriously. And
Good.
Dyson explanation is that both men had to believe the only work was serious was theorist time, was discovering the fundamental equations. And the once you had the right equation, working out particular solution was in other one, second-rate physicist or PhD student.
Yeah, that is a bit exaggerated, because after all, once Schwarzschild found his solution, it took few years to, or not even long, maybe he himself started it, to find out what is the behavior of light when it bends, when it passes the sun, or how what is the precession. Okay, precession is different, but Schwarzschild black hole solution is the solution of the gravitational field around any symmetric body, spherically symmetric body in vacuum. So that is the solution you should use. If you want to ask whether light bends around the sun, you just take the Schwarzschild solution of the sun. You don't have to worry about black hole, because the Schwarzschild radius of the sun is deep inside and there's no vacuum there. So there's no black hole. But outside, Schwarzschild solution is valid outside. Now that, as you say, it's work of second-rate physicists according to some. But Schwarzschild managed to find this. Einstein himself never thought that there will be an analytic solution. His equations are so complicated, and Schwarzschild solution is utterly simple. The equation, the function which he writes, you probably have seen it. It's utterly simple function. 1 minus 2 gm by r. Which physics student, even in ninth standard, has difficulty to understand what that thing is? Understanding the meaning, I know it's more difficult, but understanding that solution, it's nothing difficult. And that was a fabulous achievement of Schwarzschild to really do that. So I
Even
wouldn't
if you
really.
even if you look at Raychaudhuri and Penrose work, so they were exactly doing the routine work, which
Yes.
Einstein said that second-rate physicists would do. And we all
Yeah,
know
yeah,
that
because
Raychaudhuri.
correct. They never changed Einstein's equation. Once he wrote his equation, everything was routine from that point of view.
So, is there a real temperamental split in physics between people who choose, chase fundamental equation and people who take equations that already exist completely seriously and, follow them somewhere uncomfortable? So,
That's a very
you know,
good question.
and so, if there is, which ones, are you?
So, you know, the problem is the following. If you, it's a to try and understand the fundamental equation or formulate fundamental equation is a very, very high risk problem. Almost everybody in history who has tried to formulate a fundamental equation has failed and gone into oblivion.
Yeah,
Einstein, on the other hand, A, he was very smart. B, he was very philosophical but grounded. I think that's a very unique quality he had. A lot of people are philosophical. They say, oh, time may be slowing down. What if I move in a tram at the speed of light, blah, blah, blah. That, those philosophical musings he had while going to office in Bern, a lot of people might have had. But he was grounded. He tried to convert his philosophical thoughts into equations. That is the step many people miss. And then the problem is the time has to be ripe when the equation is not known and it is available to be known. That's not so obvious. After all, what has ever happened beyond the Einstein equation? You might say that few approaches to quantum gravity, including string theory and maybe loop quantum gravity, at least they try to formulate some fundamental new equations which reduced to Einstein in a special case. So it is new and it is conceptual. But how many people really formulate those equations and how many people study them? For example, today we would not be talking of superstring theory if Green and
yeah.
Schwartz had not done in 1984 a seminal, really, you might say, boring, technical, painful piece of work to try and find out which gauge groups admit cancelled anomaly and give a consistent quantum theory. It's a kind of thing that, Einstein might say, oh, this is just, some donkey work or second rate detail based on the existing theories to pick out the right one. But they found that there are only two solutions, and that one of those solutions actually gives a kind of phenomenology in four dimensions, which has broadly positive features. So, I think the second kind is what most people can think of doing. Again, now, Maldacena did something of the first kind. He formulated
Yeah.
ADS CFT, which was a new idea, though, by the way, all kind of some basic forms of it were already floating around for a long time. But like Einstein, I would say he had the philosophical grounding that maybe gravity is dual to a field theory, and then he had the equations and the examples. Without that, without that, people like 't Hooft and Susskind had said many of those words. In fact, Maldacena and Polyakov, and Maldacena was inspired by all of them, but he went one step further. But when you say Penrose and Hawking did this kind of difficult work based on existing equations, I would say, first of all, to some extent, that is true of Penrose because he basically took classical gravity and found a very important conclusion. But Hawking's work on black hole thermodynamics, that is the next level. That is Hawking and Bekenstein,
Yeah,
of which
Wittgenstein.
Bekenstein had the philosophical ideas and the conjecture, but he didn't have the method. And Hawking found the method, and that was again Einstein like. It was the conceptual philosophical framework followed by a hard calculation. And in every case, Einstein, now, people might laugh that I compare these three people, but I would say Einstein, Maldacena, and Hawking, their paper starts with something. First chapter, you might think that this is all a lot of blah blah ideas. Okay. But the second section of the paper does something, and you're like, my God, they can do that. And it means that their philosophical ideas are grounded in actual equations. And by the time you finish reading their paper, you're like, my God, this person has changed the field. And it's true of these three papers. Each of them changed the field.
Yeah. So,
But
yeah, please,
just
please.
one thing I want to say, especially because maybe many of your followers are from India or Indian subcontinent, there's a very, very bad cultural ethos in India. Of course, many good students don't have it, but it's a very, very bad cultural ethos. Bad in the sense very negative for science, which says that only the philosophical idea has value, and all this donkey work of solving the equations, writing out solutions, checking for errors, looking at their numerical evolution, finding special cases, that is all not worth doing. This is an awful way of thinking, and let me say very clearly, this is not shared by either Chinese or Americans, and this is why Chinese are where Chinese are and Americans are where Americans are, or where they got. Because there the work ethic is that nothing is too small for me to do.
Yeah,
And I was trained in that ethic because I spent 6 months of my PhD trying to find one factor of 2 with no help. My advisor refused to do the calculation for me. He said,
yeah,
there's a missing factor of 2, you find it, please. Turned out he was wrong and I was right. There was no missing factor of 2, and it corrected his mistaken theory eventually. And which is, I consider, a nice achievement. But I also learned that by working honestly day and night on that factor, so that every day I could go back to him and say, no, the calculation is correct. And hearing that and seeing me demonstrate it, he finally accepted that actually they had made a hasty prediction, which was wrong, and the paper that he had written with a different student had a fundamental flaw in the draft, and it had to be completely revised. This is very important.
yeah, because
So,
yeah, because
my thesis was that donkey work, if you like, but I'm very proud of it because it actually changed a small thing in the subject, which became important.
you were doing the routine work which
I was
Einstein or Oppenheimer
calculating
said.
I was calculating two loop Feynman diagrams in 2 dimensions by hand.
Yeah,
That's it. For those who know what are Feynman diagrams, that's what I was doing.
yeah. Feynman diagrams
Uh,
are like when particles collide with each other. Quantum electrodynamics.
hmm. Yes, exactly.
So,
It
so
uh,
can you
it 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 gives you the higher order corrections to any quantum process.
can you explain me a little bit what you were doing at the time?
Yeah. Okay. This is. I'll try to condense it. The big deal of the 19 from quantum electrodynamics time onward, since you brought it up, was that quantum field theory looks very good. It describes interaction of photons and electrons. Later, positrons got added to it. It works fine with positrons actually came with it. It works beautifully. But as soon as you try to calculate the quantum correction to a process like electron scattering or electron positron scattering, which is called Bhabha scattering, or I don't know, electron photon scattering, which is Compton scattering. The lowest order calculation is simple, but it was already, I mean, simple reasonably, but it was already known. The genius of quantum electrodynamics is that it allows you to calculate the higher ones. But unfortunately, the moment you calculate it, you get infinity as the answer. You get an integral which has the form dx upon x from some lower limit up to infinity. And as we know, dx upon x, if you integrate, you get log x. And then when x goes to infinity, it's log of infinity, which is infinity. And this is supposed to, on the contrary, be a small correction. Quantum correction is supposed to be a small change in behavior of some atomic level. And how can it be infinity? And for this reason, people, Dyson was one, Salam was another, who developed this renormalization program, which was a program to try and deal with this problem. They were successful, though the steps were slightly arbitrary and they became clearer only many years later with Ken Wilson and lot of developments. But whatever they did, however arbitrary, it was a definite prescription, it gave definite answers, and then those answers like Lamb shift and so on, those could be compared directly with experiment and it worked great. Now, in the 70s, people noticed that supersymmetric field theories, which have an extra symmetry between bosons and fermions, they are less likely to have these divergences in the first place. The divergences seem to cancel out. So, if electrodynamics has a divergent term like integral dx by dx, the supersymmetric theory will have the term integral dx by dx minus the same integral dx by dx. One will come from the bosons in the theory, one will come from the fermions, and the difference between them is zero. So divergence gone. Renormalization not necessary. This is a very oversimplified statement, but people thought supersymmetry is so exciting because it makes renormalization possibly unnecessary, and therefore maybe we can apply it to the problem of gravity where renormalization anyway never worked. Now, my advisor thought let's try this in 2 dimensions instead of 4 because 4 space-time dimensions is the real world, but it's really too difficult. So he said, let's try to see where the divergences cancel under what conditions in some 2-dimensional field theories. Now, 2-dimensional field theory is not a completely unrespectable field of research because condensed matter systems often they can be 2-dimensional, like an array of magnets. And in the limit of continuous limit, they start to behave like a 2-dimensional field theory. So whatever you learn about 2D field theory, you could apply to those systems. And in fact, Kadanoff and Wilson did exactly that with their lives. So my advisor said, try similar calculations about these divergent terms using Feynman diagrams, but in a 2-dimensional theory. Moreover, for that theory, the one loop, that is the first order correction, was already calculated. I had to calculate the second order correction. Now, anyone who knows how to calculate any corrections in perturbation theory, like maybe any BSc student doing or MSc student doing quantum mechanics, knows that first order is fairly easy, second order is really hard. Second order graphs are just second order onwards. Everything after second order is very hard. So that's what I was to do, but because it was 2-dimensional, maybe it's easier. And he was looking for a class of theories where the divergence is 0.
Yeah.
And so I was supposed to find what I told you, integral dx by dx minus integral dx by dx, but both have some number in front. And if that number is equal, they cancel. If that number is not equal, they don't cancel. And my calculation was giving the first number is 1 and second number is minus half, not 1. So 1 minus half, it doesn't cancel. Still divergent. Yeah. And he wasn't expecting that. And he asked me to find the factor of 2. There's no factor of 2. In fact, that divergence doesn't cancel. But what was understood later using the ideas of Ken Wilson was that it's not supposed to cancel. It's a kind of derived effect from the one loop or the first order divergence. And it's supposed to be exactly what I was finding. And so only when you cancel the one loop divergence, then the two loop divergence also cancels. So in a way, I was finding an echo of something which was already known, and that was supposed to be there. In fact, if I had fudged and said that, no, this half is really a 1 and the divergence cancel, it would have been a wrong result in that theory. Now, this was of interest to absolutely nobody, I should say, because two-dimensional model, some calculation, some two-loop, something. But within 4 years of my thesis, the string theory explosion happened.
Yeah.
And suddenly people realized that the model in which I did this calculation is the correct model of the world sheet of the string, the sheet swept out by a string as it propagates in spacetime. Now suddenly it gets a physical interpretation. And for string theory to make sense, the divergences on the world sheet must cancel. Must cancel. It's not an option. And I had found that condition exactly. So it was a technical, brute force, useless piece of work. And in 4 years, it now
No, it
suddenly
was not
became
useless.
applicable to a problem of not just interest, but enormous interest. I think the paper has more than 500 citations today. And most of
Yeah,
them were picked up from 1984. Within a small number of years, the citations surged into the hundreds. And I do want to say here that the paper has 3 authors, my advisor, one other student, and myself. But the calculation was actually done entirely. I mean, the advisor gave all the framework, what to do, how to do, and he talked to me regularly. But it was really my calculation. That was my calculation. And neither of the other two actually ever checked it. They
that's what
because
happened in academia.
it would have taken 2 months to check it.
Yeah,
And instead of that, they took the attitude of disbelieving it until it became clear that it might be right, and then they believed it. And then, of course, other people verified to higher 3 loops, 4 loops. A lot of things were done after that. But it was a bit of a breakthrough, small breakthrough, but a nice one. But it came as a result of this
uh,
second rate or
second
donkey.
routine work as
Routine work. It was not routine because the idea, and this for this I'll give him full credit, though he didn't do the calculation. I wouldn't have known to do this calculation. He told me to do it. Form problem was
yeah.
formulated entirely by him, and that was more important. Actually, today, if the same history was replaying and AI was there, he would just ask AI to do it, and it would be over in one day.
Yeah, so I think the way of doing physics has been changing, and the most important thing would be like how you choose the problem and what kind of problem you want to work on.
Absolutely.
So
Absolutely. And again, I want to say to your viewers, the goal is the thing, not the technique. If you are,
yeah,
if you think, well, I'm a person who only is interested in, I don't know, Feynman integrals or calculations or some type of calculation or some type of formalism, that's no good anymore. I mean, in the future, you need to be a person who says, nature is nature. What do I want to understand which I don't already understand? And then what direction can I probe which will help me understand a little bit. One has to be very humble. Whatever we do, it will be a little bit. Even Maldacena, if you see, doesn't have a Nobel Prize because he didn't
yeah,
actually explain anything about nature. But I feel sure that his work will lead to a Nobel Prize, but the time scale might be after his life or in his life. Nobody knows. But the point is that he found a direction which will teach us something about the structure of nature. And that structural question is absolutely key. So, in a way, the Indians who are all sitting around philosophizing and refusing to do calculation, now these people have got a very good tool to do the calculation for them. So, actually, philosophy of that kind becomes more important, but it can't be just verbal philosophy. I'll give you an example what is verbal philosophy. I'm sure you know this, and people have many opinions. Somebody keeps catching me and saying, but you see, this verse in the Vedas says that black holes are there.
yeah, yeah.
And I always ask them that, but please tell me that verse in the Vedas, does it find the black holes in Eddington-Finkelstein coordinates or Kruskal coordinates? And please tell me the Sanskrit name of those coordinates because I'll use it.
Yeah.
Now there's no answer because it was never found in any coordinates. It was just a idea that something like that may exist. Very good. I mean, I credit the Vedas. I have full respect for the Vedas for the philosophical speculations and some real observations about human nature and human life and nature outside us, which might have been inspired by physical observation. All that full credit, full credit. It's not the same as knowing that black holes exist in the universe,
Yeah.
which could not have come without the techniques applied to that problem, and those techniques could not have come without the original equation. Without Einstein equation, you're just talking in the air.
Yeah. So as you mentioned, the doing of physics has been changing, and calculations will be easy doing. So how would the next generation of physicists would be trained? Because
I think they'll be trained by interacting with AI. That's the main thing. Their training is given a task, ask AI to do it. But you see, AI will only do the task which you tell it.
yeah,
Right? Now I take a batch of 10 students and I tell them my task is to, I don't know, classify three-dimensional manifolds or something of certain type. Each student is asked to type a prompt into AI. They'll all type different sentence, right? Because the student will hear me and then type the prompt into AI. But how good is their prompt? And what do they do after typing the prompt? The first time they give the prompt, AI will say, well, that's a very difficult question. I don't know how to do it. Now the student has to say, okay, what do you know? What is already known? So AI will tell you that, from reading all of the existing internet, this much is known, this much is known. Very good. Then you have to come up with a good question. Can we, if we can't classify the full set of such manifolds, can we define a subclass which is interesting, about which not much is known, and we classify only the subclass? This, by the way, this happened 1 week ago. You might have heard there's a Riemann hypothesis in
yeah,
mathematics, which
yeah,
says that the zeros of the points where a function, zeta function, goes to zero, the Riemann zeta function, all lie on a particular axis. All of them. Now, it was already known that roughly 40% of them lie, I mean, it has been proved over decades by donkey work that 40% of them already lie on that axis. But, the theorem is that all lie on the axis. Till that time, you have not solved the conjecture. But 1 week ago, I think one of the AIs was able, by prompting by a person who found a proof that 65% of the zeros lie on that axis, not
yeah,
41%. So we came closer to the proof. Now, my question is, what stopped you and me from doing that? Most likely this person, though obviously they had a passion in maths, they're probably, okay, you and me are not maybe mathematicians, but what stopped any mathematician in TIFR or ISER Pune maths department or the DU maths department from doing it? There might be a dozen people in India who do know enough about it. They might be teaching Riemann hypothesis and its associated mathematics in a course, advanced course. They might have guided students to work on it. Why didn't they ask AI to do it? And there are two answers. One is that some of these AI results have come by using, I think this Riemann one came by using a privately available AI model which is not available to the. So this is a case where the country not having its own AI will suffer. This is where China is working very hard to make sure that they will never be denied access to American AIs, because by that time their AIs will become as good. We are, as far as I
yeah,
know, exactly nowhere in this race. This is called AI sovereignty. We are supposed to develop AI sovereignty, and we, as the one of the three big nations in the world, four: Russia, US, China, India. The sheer size of the country means we do, and we have quite a decent scientific community. Computers, we are famous for IT expertise. We should have been, I think, I'm no expert, I don't want to blame anyone, but obviously it requires a massive investment and it requires putting competent people in charge. Both of these somehow we are not doing, seems to me, most of the time. Anyway, sir, or let's put it more constructively, China is doing that much better. That's a reality.
yeah.
So
It's a
one thing
reality.
is access to the AI, but the second thing is the passion for a small result. Because after all, this person, now I'll come to this neuro person who did this Cluse's conjecture or whatever it was. It seems that every few months he was asking AI the same or related questions about this conjecture, and every time it was failing, and now because AI became better and maybe his questions became better, one fine day it succeeded and gave a proof that now mathematicians are certifying. Okay. So in his spare time, instead of watching TV or I don't know, doing whatever we do, shopping in malls, a few hours dedicated to one goal which doesn't look like it may succeed, but I feel it from my heart that this is a goal worth pursuing. I do it for myself. It can pay off.
Yeah,
And it paid off this guy. And all the people who have done this kind of discovery, now I think there are half a dozen discoveries which were done by what you can't call amateur, but not fully expert, like typically undergrad student who has
enthusiastic people.
huh?
Enthusiastic people, you can call them.
Enthusiastic, trained, of course, minimum, but not trained as highly as a faculty member, not faculty members, but with the passion. Somehow,
Yeah,
what I'm seeing is they are all either Chinese or American. Maybe I'm misrepresenting. Maybe you can go through the literature and find that maybe some other people did it, but I don't know of a single Indian who actually did that. We are very famous for building up child geniuses of all kinds.
yeah,
But it's always that they appear to be geniuses and never that, okay, they have done something genius.
yeah. This is something the government and the private enterprise need to think about right now.
I think it's not just government and private enterprise. I think this is deeply embedded in our culture, which
Yeah,
disrespects manual labor. I think, if you like, this work is a form of manual labor. So if you spill some liquid in your lab and you call the peon from the next room, say, "Aa jao, ye saaf karo." That's your way of doing your experiment. That's one. That is the disrespect, that you won't bend down and with paper, tissue, or cloth mop up the mess you made. That
yeah,
is, sorry to say, that's in our culture.
yeah.
It's going, it's decreasing, it's improving, but it's in our culture. And for better or worse, the far eastern cultures, Japan, China, all the other countries in that region, including Muslim countries like Indonesia and Malaysia, but strongly influenced by Buddhist philosophy, which really emphasizes self-help and self-responsibility.
Yeah,
And I feel that, our government could also have tried to emphasize that better than it has done in practice by showing it.
yeah.
Okay, it's not like any of our politicians is the kind who will clean up a mess if they make it. So, we need but then they are also a reflection of our society. So we need a societal change where details are important, self-help is important, self-esteem is important.
How
I'll even
that?
say one more thing. Ultimately, for our lack of self esteem, I blame the British also, because 200 years under a foreign ruler who was telling us what to do has made us a nation of people who follow orders and didn't develop the self esteem to create our own orders. And our
Yeah,
students are like that. The first thing when I meet new students in ISER is to try to explain to them why their job goes beyond following orders. I'm not saying don't follow orders. If I said, I would also get in maybe trouble, but the job deviates from just following orders.
there is something curiosity which is not in the students.
No, the curiosity is there. The system drives it out of them. The curiosity comes at age 4 and 5. The curiosity is there at age 10. Parents tell them things like, don't ask too many questions, do what you are told. The teachers tell them same thing. All this is done to make life easier for the teachers and the parents. And poor child who has got the curiosity graph is decreasing function by the time they reach college. So much so that when we get students who are fresh out of BSc, we find their curiosity level is higher than students who are out of MSc. In MSc
Yeah.
in a traditional university setup. That even in those 2 years, the curiosity has been damped out.
As you said, your advisor was wrong about the problem, and then this the the effect was you are talking about. So I want to spend more time on Raychaudhuri as a person. So in 1952 he got a research position at IACS. His director was Meghnad Saha, who did great work in stars and all, and he pushed him towards more mainstream work, and his official research become more about metals, and the general relativity was done almost on the side by him, Raychaudhuri.
Yes.
So
Yes.
do you know the pressure? What kind of pressure was that like? Was general relativity was simple and fashionable at that time in India? Can you tell a little bit story about this?
It's a very strange story because the first book that translated Einstein's paper, which was in German, into English, was actually authored by Meghnad Saha together with S.N. Bose.
Yeah.
It's called The Principle of Relativity. It was published by I have it here in front of me, the cover page, published by the University of Calcutta in 1920. That's only 5 years after the discovery. And Saha and Bose together translated from German to English. So obviously, and they were scientists, so obviously they learned what they were doing. Huh? And it has a historical introduction by Mahalanobis, another legend in mathematics or statistics. So he knew general relativity, and yet what Raychaudhuri said in later life, the quote from his diary, Raychaudhuri has a very interesting diary which is partly in Bengali and partly in English. I would love it for somebody to use maybe Google, use AI to translate the whole thing into English, because some of us are missing the subtlety.
Yeah.
And here is, I'll read from it what Raychaudhuri wrote. Uh, Dr. Saha entered into the registrar's office and told me curtly that the rules require that I must work with the head of the department, that was Saha. If I found that not to my liking, he told me to seek a job elsewhere. I met Dr. Saha on the following day. I told him that while I was prepared to work with the head of the department, I did not find his works very appealing. I love that statement because you can imagine what kind of I think in your university, go and tell some faculty member that and see how they react. Dr. Saha remarked that good work was not very plentiful, that everybody was doing more or less routine work, and that he could not quite see the utility of working either in meson field, which is the old name of particle physics, or relativity. He himself felt it would be more fruitful if we directed ourselves to problems in chemistry, which are sometimes arising in connection with the work being carried on in the physical and organic chemistry laboratories. Now, I have a slight sympathy with Saha on one point, which is that we are now in 1953. India is only 6 years old as an independent country. This happened in 53. Obviously, there's huge pressure for scientists to work for the good of the nation, and obviously physical and organic chemistry and its consequent creation of materials and techniques and medicines and compounds and all kind of things would be invaluable for a nation where the birth rate was, when the life expectancy was so poor, the health indicators were so poor. That is all true. But Saha seemed to have gone into that a little too much. And it reminds me of some of the administrators I see today who feel that a scientist has to basically bow down and obey whatever government is pushing on them, forgetting that on some issues scientists actually know better and their work will have more long-term impact. In fact, Raychaudhuri might have not saved any lives of people suffering from malnutrition. Surely I agree with that. And maybe if he had worked on metals as he was told to do, it might have created, I don't know, some kind of semiconductors or something, some device, something or other, some machinery, which could have really made a more
Beneficial.
immediate impact. But he didn't have the interest. And we do science out of interest. We can't do it under some kind of instruction and order from above. And in fact, the paper that Raychaudhuri wrote called Note on the Network Approximation in Metals has only one citation today in the literature. So it didn't even have any impact on the literature. And his famous paper of 1953, I wrongly probably said 1955 earlier, 53 December, Relativistic Cosmology 1. This paper has 1,000 citations by now.
Yeah.
And it has changed the face of cosmology, therefore, of also astronomy. And therefore, also, now again, you could say even that is not feeding poor people, but there's no either or. I mean, some people will change the face of astronomy, other people will change the face of medicine. They don't have to be the same people. There's not one size fits all. I'm very upset by the one size fits all approach today, where every institute, every physics department in India feels that material science is the only important subject and everything else is just some kind of entertainment. It's not just entertainment. And
Yeah.
as you know very well, von Röntgen discovered X-rays by accident while fooling around in the lab, and within 2 years it became a medical tool. And to this day, there's nobody alive who has never had an X-ray. You have had an X-ray, I have had an X-ray.
You
And
know,
it's a
when
standard medical tool.
yeah, when I go to Delhi University, I study in Delhi University, and when I go to the physics department, I mostly see the professor who are working in material science.
Oh,
I
they should do
genuinely,
it. They should do it. They shouldn't stop other people who are working in
yeah,
something else. And in fact, they should encourage those other people also. There's room for everybody. It's a big country.
yeah,
You're right. All the professors you see in most physics departments are working in material science or condensed matter, and they are welcome to do it. And I would never undermine what they're doing.
yeah,
On the contrary, many of them, and I'm sorry, I have a lot of names in my mind which I won't be telling you here, have tried to undermine what I do. They have no business doing that. They are doing what Saha was doing to Raychaudhuri, although I'm not Raychaudhuri. They are also not Saha. But, they have no business. But in India, we have a lot of undermining of fundamental research. And if not undermining, then disinterest. Like, oh, that's not real science. It's not real physics. Who the hell says it's not? Black holes are, the universe is full of black holes. Don't tell me it's not real physics. In my institute, even in TIFR, there were at least 15 or 20 people working in material science. There were another 10 or 15 people working in astronomy and who switched to gravitational wave astronomy, many of them. Nobody is stopping them. Nobody is saying don't do it. The mistake that Saha made was not to say that it's a good idea to work on physical and organic chemistry. It was a good idea, and today it's a good idea. The mistake was that he picked somebody who was really brilliant, and he had no business not to understand that. He treated Raychaudhuri, as
yeah,
far as I can see, like a child who needs to be given orders. And
yeah.
that's what you shouldn't do, because however your biological age, it might be 18, you might be on the verge of a breakthrough. And how can we treat all 18-year-olds as little kids and tell them you can't drink, you can't this, you can't that, you have to be in bed by 10 p.m. and then expect them at the age of 20 or 21 to come up with a revolutionary discovery? We are blocking it ourselves.
You need to give the freedom, otherwise,
To give the freedom, and we need to accept that the freedom may be abused by some people. You see, we spend all our time worrying about the people who abuse freedom. Let's say we allow a lot of things on a campus. Suddenly we find somebody has brought alcohol or something. Then suddenly we start heavy security check, locked this thing, nighttime curfew, blah, blah, blah. In the process, we are killing the good things that can happen for the sake of two or three. If you have some students creating a problem, deal with those students.
yeah,
But we
yeah,
always make the law to deal with all students as if they are some kind of irresponsible babies. And this is
yeah,
actually well known. It's called patriarchy, the whole idea of design of society where the father treats the children as children always, and the children have to treat the father as father always, no matter that father may be wrong about something. We are all trying to be fathers to the children. And I don't want to go into politics, but you know that this is not working very well nowadays. And suddenly, politicians have discovered the virtue of saying that no, no, our youth are very important to the country. Good, they should have said it long ago.
yeah. So, Raychaudhuri's most famous student at Presidency College was Ashok Sen. The same Ashok Sen you later collaborated with. Did your paths ever crossed through him? Like, did Ashok Sen ever talk about what Raychaudhuri was like as a teacher?
Actually, actually, he didn't, and I actually have never talked with him about it. Though I meet him often. I even met him last weekend. We had a little holiday together. We meet very often, but I forgot. I've never really sat him down and asked, and I should. But Ashok is not a chatterbox. He is a quiet person who
Yeah,
does a
yeah,
lot of work,
yeah,
and I'm the chatterbox. So, well, that's how it is. But he definitely was Raichaudhuri's most successful student, but not only one, I'm sure.
yeah.
For
Not only
example,
one, of course. Yeah,
I think Shumit Das must have also been his student. I think even I have colleagues here in ISER Pune who were his students. Different people took away different things. I have heard a lovely story from Probir Roy, who's no more now,
yeah,
who was my colleague in TIFR, who said that they used to admire Raichaudhuri and they wondered what is the secret of his incredible brain. And they found that every day he goes and eats this chana chur.
yeah, yeah, yeah. I heard the story. Yeah,
And then they decided that they must go and do that in order to become smart like him.
yeah. It was
So he
like,
had all. Yeah,
yeah, it was in the documentary that produced by Ayuka and Vigyan Prasad, I think.
I see, I see. So, in fact, Raichaudhuri influenced a lot of people. And the only thing I feel sad about is that because of this pressure, he only essentially wrote this one paper. But what he should have deserved was at that time immediately a fellowship to go to Cambridge, which was the heart of this activity, or Oxford, and spend time. Now, of course, Ramanujam famously went to Cambridge, but that's because of Hardy's efforts to get him there. And maybe Penrose and Hawking didn't want to, or didn't. I don't know. It's nobody's duty. I mean, it's our system's duty to send our good people in the place where they will flourish. And obviously, this pressure caused him to change his job and basically position himself more as a teacher. And he could not have done what Penrose and Hawking did because they were in the presence of so many people. I mean, Sharma, Bondi, and all Sachs from America. They would also come and meet. They would come and spend time in the UK. Weinberg spent time in the UK. So many great people around in that environment, you can deliver your best. Raichaudhuri delivered, I think, what is the best that a completely isolated person can deliver.
So from Einstein to Raychaudhuri to Penrose and Hawking, what does this history teach us about physics as a human activity?
I think it teaches us that passion for fundamental laws always pays off. For me, as a string theorist, it inspires me because it may be that in my lifetime I don't get to see that string theory is a reality of nature. But then probably many people, I don't know, Oppenheimer or whoever, might also have not lived to see that black holes became a routine object in a way in the universe, and that every galaxy has a supermassive black hole. What a fantastic result! Many people died. Einstein did not ever get to know that. Obviously, he died in 55.
And Hawking like was died in 2018, and in 2019, I guess, or 2020, we got the picture of black hole.
Yes, but the picture of black hole is, of course, a bit overblown. It's not as important to the
Yeah, yeah,
understanding.
but
This is more like a nice observation. It's not even a picture of black hole, picture of the light outside the black
yeah,
hole.
picture
But
of light outside the black hole.
nice, of course, but he never got to see it. Correct. And now Hawking predicted Hawking radiation, and he's dead. And maybe someday somebody will find an ingenious experimental way to detect it, and then Hawking would deserve a Nobel Prize, but it would be too late. So that's all right. What I'm inspired by is Hawking and Penrose never cared what people thought of them. They just did it because they wanted to do it.
Yeah,
Feynman even wrote a book saying, "What do you care what people think?"
yeah, there is a
He
famous book
didn't
by Feynman.
call the book that, but it was published under that title. And
Yeah,
honestly, I feel that in the culture I grew up, I was trained to care about what people think. I had intelligent, educated parents, but I was highly trained to care what people think, and I have a very sensitive nature. And probably I could never, even if I had the brains of those people, have done the work like Hawking and Penrose, because I care too much what people think. But the converse duty is that people also should not run you down. People should say, oh, wow, you're doing something really interesting. If it succeeds, it will be a fantastic payoff, but anyway, it's worth the effort. That is what we should tell a person who's embarking on something really blue sky, very not yet formed ideas and questions. But as I said, it's ultimately about questions. Hawking's question was, what is at the beginning of the universe? Hawking's question was, do black holes form and what is in their center? These are big questions. Raychaudhuri's question was, what is the right formalism to transport general relativity into a form where we understand trajectories, flows in time? Not fluid flows, but flows in time.
Yeah, so from the background of your room, I can see some pictures of music, I guess.
Uh,
So there is a huge history of physics with the music. Einstein
yeah,
was a pianist, I guess, what we
yeah.
call the violin, and Satyendra Bose was also interested in music. So I think this history is very connected with physics and music, and I think it will never end.
I hope so. I hope it doesn't end. But it could also be that it just connects to the emotions of certain types of people. I couldn't find any real connection between my love of music, which is like many kinds of, you see classical musicians here, but if I turn my laptop, you will see my electric guitar sitting over there. And that's what I was playing just before we met. And you can see the mess of my amplifier and guitar processor and some more guitars.
Yeah,
So, everybody has their passions. They don't
yeah.
always intersect. They are just, in fact, I play guitar when I want to clear my head out of physics and just think of something else.
This is really interesting. This is really good. So thank you, Professor, for joining us today and telling the story of Raychaudhuri and the history of this general relativity and how the theories arise in culture. Thank you so much for doing this.
Thank you, Ayush, for creating a platform where interested students can really tune in and look at things which are of interest to them. I think it's a great job you're doing, so please keep doing it.
Thank you.